So here, starting from this slide, I'm going to talk about the factor of the safety. And this is in our very last section in chapter 1. But here I kind of put it up and earlier for discussions. The factor of the safety basically is defined by this. And again, here in term, this should be sigma in Roman characters, sigma u, sigma allowable. And that is the definition to define the factor of the safety. And let me say what is the sigma u. The sigma u, basically, this is the Roman characters in sigma u. Sigma u can be obtained by material testing. Material testing basically is the material under uniaxial loading. For example, for this sample, we apply the loading in this way, and slowly, eventually, once we keep applying the loading to break this material, eventually material will break like this, and we denote the loading conditions. So that means during the loading conditions, we simply record what will be the maximum stress this sample will experience, and that is here. This is a peak of the stress it will experience. Then we define that as sigma u, ultimate stress. Okay, this means ultimate stress. And ultimate stress basically is one of the material properties. Once we select, say, aluminum, then aluminum will look at the data book of the aluminum. We should be able to find the sigma u for aluminum. For example, if we're going to find using the stainless steel, then the stainless steel should have its own the magnitude of sigma u. So once you determine a material, then this value has been determined. That is the nature of the material properties. So now you can see, right now you can get a feeling about the factor of the safety. The factor of safety is in this. For example, once you select a material, and then this material will be used for carrying certain loading, you don't want to risk your structure to be broken like this. So that means to avoid the kind of risking, you usually say, I want the maximum loading of my design be, say, 10 times smaller than the ultimate stress. So that means this 10 times give yourself the safety margin. So that means here you can see, if, say, you pick this material as the aluminum, okay, aluminum, for example, the ultimate stress is 60 KSI. Then I said, well, I don't want to risk my aluminum structure be pushing that limit. I want to be more safe, more conservative, so I select my factor of safety equal to 10. So that means 60 divided by your selection 10 equal to 6. So 6 KSI will be the maximum stress your design is allowed to carry. So the concept is this. Once you pick material, the sigma u is the nature of the material property that is determined. Then you, as a designer, you select your factor of the safety to determine the allowable stress that your structure can be maximally loaded up. So here again, if you choose your allowable stress, or in turn you select your factor of the safety, either way, those are the designer preferred the design data. Okay. And so that is the allowable stress. And here in this chapter, we define it using allowed or allowable. Okay. So back to our previous example, the bar BC is made of the steel. And what is bar BC? We look at the previous example here. So this is our bar BC. So for this example, we choose steel as the material. So for steel as a material, then we look at the sigma, the steel data book. Then we have the sigma u. And sigma u, we define our factor of the safety. Then this will be our allowable stress by definition. And now for this design, we simply say this value is 165 MPa. Okay, so this is a result of this calculation. for this example, probably we are not given this value, we are not given this value, but we are given this value. Okay. So this is our design criteria. And what that means, allowable stress. Allowable stress, that means this should be the upper limit. That should be greater than or equal to all the possible maximum stress will be experienced by your design. So from our previous example, from this calculation, our calculation is 159 MPa. And I'm asking you what this loading, so if this structure using steel, given this dimension to carry 30 kilonewtons, is this portion safe per your design? And Jennifer, you should reply, yes or no?
Yes.
Yes, because this calculated result is 159, which is lower than allowable. Allowable is our maximum cap designed. So this one is safe. Okay. So that is the concept. So for our case, because this one is still greater than 159 MPa calculated here, so here is, we say safe. Okay. So now the remaining, the similar question is this. If I would raise our loading from 30 to 35, is this design in this portion BC still safe? We can do a little bit calculations. So for this scenario, the stress in BC, because the stress is proportional to the magnitude of the force. So that means for our original 159 MPa is respect to 30 kilonewtons, and right now we raised up to 35. So right now our stress will be linearly increased by this much, right?
Mm-hmm.
Okay, so this one we can calculate. I think this one is 168 MPa. This one is 186 MPa. So now if we increase our loading from 30 to 35, then in this portion, we calculated the stress is becomes 186. So this value exceeds the allowable stress, which is 165. So that means this value exceeds the maximum allowable stress you defined. So that means it will risk your design. We don't know when the material here would fail, but right now it's kind of deteriorate your confidence of the design, because you, in your design, you choose this one, the maximum allowable stress is 165. Okay, so you might kind of considering, okay, I might need to reduce the loading from 35 to maybe 31 or 32. Or the other option is you have to increase the diameter of this portion to be safer. Okay, so that is the things. So here, as long as the stress in BC is less than the allowable stress, everything should be safe. Okay, no failure concern. And the second related option is this. Still, we consider the same structures and carrying the same magnitude of the loading. And here, the previous example is we choose steel. And right now, for this option, we replace the steel by aluminum. We see what happened. Okay. And we look at the aluminum data book, and then we select our factor of the safety. And right now, we found for aluminum, we have the allowable stress is only 100 MPa. Okay, that is our design criteria. So under these situations, carry 30 newtons, and we found our stress in this portion is 159. This value, the stress in this portion is 159. 159 exceeds the allowable stress for aluminum 100. So that means if we're going to replace the aluminum, say, we replace steel by aluminum in this for this portion, carrying the same loading, then this portion is have a risk in failure. Okay, it has a risk. It won't fail right away, but it has a risk, has a concern. Okay, so the one way, the couple options we can help to resolve these kind of failure issues. One is to reduce the loading. Probably your boss won't be happy about this one. The other one is to increase the material property, increasing the cross-sectional area, which means money. You need to buy more materials, spend more costs. Your boss won't be liking this one. So maybe the better way is to maybe change back to steel or other stronger material, and which means try to raise your the allowable stress higher. Okay, so that is the applications for this, and we stop here.